Welcome to Social Work 240 Session 6. The topics of this session include an introduction to inferential statistics and definitions and examples of the independent samples t-test and the dependent samples t-test. The process of quantitative data analysis involves two types of statistics. Researchers usually start a statistical analysis by examining the descriptive statistics for all of the variables of interest in their study. So that would be the independent and the dependent variables, and also any extraneous variables that could be important because of their influence on the independent and the dependent variables. Inferential statistics are used to test hypotheses about the relationship between the independent and the dependent variables. There are two broad types of variables. The first are categorical variables, which are variables that are categories with no numerical value. There are two types of categorical variables, nominal and ordinal. Nominal variables are those that have no ranking and are just a category, such as gender, race, ethnicity, place of birth, etc. Ordinal variables are categories with a ranking, but with no equal distance between categories, such as education level, income level, or Likert scales that include strongly agree, etc. Continuous variables are those that have a numerical value associated with them and that also have equal distances between values, such as age, height, weight, number of hours studying in a day, etc. The type of inferential statistic that is chosen in order to test a hypothesis depends on the type of independent and dependent variables that are measured. Inferential statistics are used to test hypotheses. If we get a statistically significant result after testing a hypothesis, then we say that it is unlikely that the relationship between the independent variable and the dependent variable is due to chance, which then means that we can be reasonably confident that the independent variable is actually related to the dependent variable. But what does it mean to be reasonably confident that there is actually a relationship between the independent variable and the dependent variable? When we use inferential statistics, we use terms like reasonably confident or unlikely to be due to chance, because all inferential statistics are based on probability theory. Probability theory allows us to indicate the likelihood of a relationship between an independent and a dependent variable within a given probability of error. This means that inferential statistics never prove anything. Instead, they give us guidelines in order to decide whether there is a strong probability that there is a relationship between an independent variable and a dependent variable. In addition, inferential statistics also do not prove a cause and effect relationship between the independent and the dependent variables. If we use inferential statistics and find that there is a statistically significant relationship between the independent and the dependent variables, this does not necessarily mean that the independent variable is causing the dependent variable. Remember the three conditions that need to be met in order to say that one thing causes another thing, which include time ordering of the variables. The independent variable has to come before the dependent variable. An empirical association, which is our inferential statistics, and elimination of extraneous variables as alternative explanations. Inferential statistics address condition number 2 and can demonstrate an empirical association between variables. There are some types of inferential statistics that also address condition number 3, elimination of extraneous variables as alternative explanations for an empirical association between variables. When you are testing a hypothesis using inferential statistics, what you are actually testing is whether a relationship between an independent and a dependent variable is due to chance or unlikely to be due to chance. So within inferential statistics, we separate a hypothesis into two components. The null hypothesis, which states that a relationship between an independent and a dependent variable is due to chance. In other words, there is not really a true relationship between the independent and the dependent variables. And secondly, the alternative hypothesis, which states that the relationship between an independent variable and a dependent variable is not due to chance. In other words, there really is a true relationship between the independent and the dependent variables. When using inferential statistics, we don't say that the alternative hypothesis is proven or true. We say that we fail to reject the null hypothesis. So how do inferential statistics work? All different types of inferential statistics result in a test statistic, which is a number. Probability theory allows us to produce test statistics from the data collected in a study. Test statistics are a number that are used to decide whether to accept or reject the null hypothesis. Therefore, the decision to accept or reject the null hypothesis is based on probability theory. There are different types of inferential statistics that produce different types of test statistics. The type of inferential statistical test that a researcher chooses depends on the type of independent and dependent variable, whether it's categorical or continuous. We are going to learn about the t-test, chi-square, ANOVA, correlation, and linear regression. The process of using a test statistic to accept or reject the null hypothesis involves the plotting of that test statistic on what is called the normal distribution. When a test statistic is plotted on a normal distribution, it can be associated with a probability or a likelihood that that value would have been produced had there been no relationship between the independent and the dependent variable. We will look at an example of how this works in relation to the t-test in a moment. A normal distribution is a theoretical, or in other words, based on probability theory, bell-shaped curve. The normal distribution is sometimes called the normal curve or the bell curve. This is because of the bell-like shape that results when data that conform to the normal distribution are plotted on a graph. This is demonstrated in the picture on the slide. Notice that the curve is concentrated in the center and then decreases in a symmetrical fashion on either side. Because of this symmetrical shape, probabilities about the likelihood of finding a value on a test statistic can be calculated. Although this picture represents a theoretical normal distribution, it turns out that many continuous variables will follow this pattern when enough data are collected. For instance, if a researcher collects a sample of measurements on variables like height, weight, SAT scores, IQ scores, and many other variables, and then plots the values of these variables, the resulting graph will follow a pattern similar to the normal curve. The middle line in the graph represents the mean or the average value of a variable within a sample of people. The additional lines in the normal distribution graph represent standard deviations. A standard deviation is a number that reflects how much variation there is from the average value in the data set. Standard deviations can be quantified and plotted on a distribution, and when data follow a normal distribution, standard deviations correspond to a specific probability of that value occurring. Researchers use the normal distribution in inferential statistics as a way to make a determination about whether or not a test statistic that was found in a study was unlikely to have been found by chance. This is done through the use of a computer program that calculates a test statistic based on the values of a variable in a data set. This test statistic is assumed to follow the laws of probability theory in relation to the normal distribution. In other words, how values are distributed within a population of people. When a test statistic is plotted on the normal distribution and the test statistic falls within a specified rejection region, then we reject the null hypothesis, which implicitly means we accept the alternative hypothesis and conclude that a relationship between the independent variable and the dependent variable is unlikely to be due to chance. The rejection region is determined by the researcher prior to conducting the statistical test and is called the alpha level. In the social sciences, the maximum alpha level, or in other words, rejection region on the normal distribution, is usually 5%, which is usually split in half to be 2.5% on either side of the normal distribution. This means that if a test statistic, which is a number, is plotted on the normal distribution and that test statistic falls within either rejection region on the normal distribution, then we conclude that it is unlikely that a relationship between an independent variable and a dependent variable is due to chance, and we reject the null hypothesis, which means we implicitly accept the alternative hypothesis and conclude that there is a relationship between the independent variable and the dependent variable. When you plot a test statistic on the normal distribution, the location of that test statistic on the normal distribution is associated with a p-value, or a probability. If the p-value produced by the test statistic is within the rejection region on the normal distribution, then you reject the null hypothesis and conclude that there is a relationship between the independent and the dependent variables. Let's look at an example of how these concepts work in relation to the t-test. The t-test is an inferential statistical test that is used to test a hypothesis when the following conditions apply. The first is that the independent variable is categorical and has only two categories. And the second is that the dependent variable is continuous. There are two types of t-tests. The independent samples t-test, which compares the means of two samples that are not related, or two different groups, and the dependent samples t-test, which compares the means of two samples that are related, usually the same person in the form of a pre-test and a post-test. First, we'll look at an example of the independent samples t-test. A team of researchers are assessing the impact of an intervention focused on engaging older adults in recreational activities, including trips into the community, exercise classes, and opportunities to increase their social networks. One outcome, or in other words, the dependent variable of the intervention, is to reduce depression among older adults. The sample includes 32 people who participate in the intervention and 28 who do not participate in the intervention, considered the comparison group. After 3 months, all 60 older adults complete a self-administered survey measuring depression levels that is scored on a continuous scale from 0 to 30, with a score of 0 indicating no depression and a score of 30 indicating a high level of depression. This is an example of a pre-experimental group research design. There are 2 groups, but no pre-test, just a post-test. So let's deconstruct this research scenario. The hypothesis for this research scenario is, it is hypothesized that the intervention group will have lower levels of depression than the comparison group. We expect that if older adults are participating in recreational activities, which include opportunities for increasing social networks, that this could improve mood and reduce depression. The independent variable is participation in the intervention or not, which is a categorical variable. The variable is expressed as either the intervention group or the comparison group. The dependent variable is the score on a depression survey, which is a continuous variable. The independent samples t-test is the appropriate statistical test for this hypothesis because the independent variable is categorical with 2 categories, and the dependent variable is continuous. After the researchers collect the survey data from the participants, they enter these data into a computer program in order to generate descriptive statistics and the t-test. When evaluating the results of an independent t-test, some of the key things to consider are: what are the mean values within each of the two groups? These are the descriptive statistics that give us information about how different or similar these values are. In this example, the intervention group has a score of 14.56 on a depression survey, and the comparison group has a score of 14.86 on the same depression survey. So just looking at these values, it doesn't look like the intervention group's level of depression was much lower than the comparison group's level of depression. The second thing to examine is the t-test statistic and the p-value. In this example, the t-test statistic was calculated by the computer program to be negative 0.136, and the p-value that was associated with this t-statistic was 0.892. If this t-test statistic were plotted on the normal distribution, it would be very close to zero, which represents 0 standard deviations from the mean. It does not fall within the rejection regions, which means we fail to reject the null hypothesis, or we implicitly accept the null hypothesis and conclude that there is no relationship between the independent variable, which is participation or not in the intervention, and the dependent variable, which are the scores on the depression survey. Each test statistic has an associated p-value. The p-value reflects a probability that the relationship between the independent variable and the dependent variable was due to chance. Because we found no statistically significant difference between the average depression score in the intervention group and the average depression score in the comparison group, we could conclude that this intervention has little impact on the depression levels of older adults. However, there may be alternative explanations for the results. It is possible that the intervention was not long enough to have an impact on depression levels. There could be problems with the validity of the depression measurement used. And because there was no random assignment to the treatment conditions, it is possible that characteristics unique to the study participants are responsible for the lack of significant differences. In addition, there is no pre-test measure of depression, so we don't know how the intervention group may have changed. One of the problems with the research design in the previous example is that we cannot determine the time ordering of the independent and the dependent variables, because there is just one point of data collection, and that is the post-test for both groups. This research design could be strengthened by including a pre-test for both groups, so that we could determine whether or not depression levels changed after people began participation in the intervention. If a pretest were added, we could then conduct a dependent samples t-test with the intervention group and a dependent samples t-test with the comparison group to test the hypothesis that depression levels among the intervention group will show greater decline than depression levels within the comparison group. If we examine the research question in this way, then we can first conduct a dependent samples t-test with the intervention group. Let's imagine that the average pre-test depression score among the intervention group was 18.1, and the average post-test depression score among the intervention group was 14.5. The t-statistic is negative 6.487, and the p-value is smaller than 0.001. If this t-test statistic were plotted on the normal distribution, it would be well within the rejection region, and the p-value is less than 0.05, which is the alpha level. So we would consider this to be a statistically significant finding, which means that the mean depression score at post-test for the intervention group was significantly lower than the mean pretest depression score. We then repeat this process with the comparison group and we get these results: a mean pretest depression score of 14.7 and a mean post-test depression score of 14.9. The t-statistic is negative 0.701 and the p-value is 0.490. If this t-statistic were plotted on the normal distribution, it would not be within the rejection region, and the p-value of 0.490 is greater than the alpha level of 0.05, so we therefore fail to reject the null hypothesis and conclude that there is no statistically significant relationship between the independent and the dependent variables, which in this case means that the pretest depression score of the people in the comparison group was not significantly different from the post-test score. This example illustrates that when a pretest was added to the research design, the dependent samples t-test indicated that the intervention group showed a greater decline in depression levels than the comparison group, which showed no significant change. There are still limitations to this example. For instance, the intervention and the comparison groups were not randomly assigned to conditions, so it is still possible that the intervention group is different in some important way than the comparison group. In addition, there could also be extraneous variables that are influencing the change in the depression score in the intervention group. This concludes session 6, income level, or Likert scales that include strongly agree, etc. Continuous variables are those that have a numerical value associated with them and that also have equal distances between values, such as age, height, weight, number of hours studying in a day, etc. The type of inferential statistic that is chosen in order to test a hypothesis depends on the type of categorical variables, which are variables that are categories with no numerical value. There are two types of categorical variables, nominal and ordinal. Nominal variables are those that have no ranking and are just a category, such as gender, race, ethnicity, place of birth, etc. Ordinal variables are categories with a ranking, but with no equal distance between categories, such as education level, income. Welcome to Social Work 240 Session 6. The topics of this session include an introduction to inferential statistics and definitions and examples of the independent samples t-test and the dependent samples t-test. The process of quantitative data analysis involves two types of statistics. Researchers usually start a statistical analysis by examining the descriptive statistics for all of the variables of interest in their study. So that would be the independent and the dependent variables, and also any extraneous variables that could be important because of their influence on the independent and the dependent variables. Inferential statistics are used to test hypotheses about the relationship between the independent and the dependent variables. There are two broad types of variables. The first are category independent and dependent variables that are measured. Inferential statistics are used to test hypotheses. If we get a statistically significant result after testing a hypothesis, then we say that it is unlikely that the relationship between the independent variable and the dependent variable is due to chance, which then means that we can be